In this video, we learn how to compute the electric field energy density in the presence of a dielectric. So we're going to do this in the context of a parallel plate capacitor. So we have a classic parallel plate capacitor here with a plate area of A, plate separation distance D, and potential difference of V across those plates. And we can see the usual uniform electric field generated between those plates pointing from the positive to negative plate. And we have a dielectric material sandwiched in there, and we've given that a dielectric constant of kappa. Again, the goal is to compute the electric field energy density. And the big idea there is that we already know how to compute the energy stored in a capacitor, but we perform a conceptual shift here and attribute that energy to the electric field itself. So the field is filling the space between the plates, and that's one way to account for the stored energy. And we're going to get an expression for the density of that energy, and that would be measured in joules per cubic meter. So to get started, we write down the total energy stored in the capacitor, and we remember that's 1/2 CV squared. Now we can calculate that capacitance based on the geometry of the capacitor and the presence of a dielectric. So we've replaced the capacitance there with kappa epsilon 0 A over D. That's how we compute capacitance based on the geometry and dielectric constant. And notice that I also replaced V with E times D. And that's how we compute a potential difference in a uniform electric field. It's just E times D. So now we're going to square that E times D, and we get E squared D squared, but one of the D's is going to cancel out. And we're left with this expression, 1/2 kappa epsilon 0 A times D times E squared. And I put the AD in parentheses because that has a geometric interpretation. A times D, just the plate area times the separation distance, is simply the volume contained between the plates of this capacitor. Now what we're after here is energy density. That's energy per unit volume between those plates. So I'm just going to divide both sides by volume. And now on the left-hand side, I've changed that to a little u, standing for energy density. Again, that would be measured in joules per cubic meter. And on the right-hand side, we have a 1/2 kappa epsilon 0 E squared. But remember, we have a special name for kappa epsilon 0, and that's called the permittivity of the material. We normally use a simple epsilon for that. And so we get this formula for the electric field energy density between the plates of the capacitor. It's just 1/2 epsilon E squared, where epsilon is the permittivity of that dielectric material. And notice that this formula is completely analogous to the formula that we got for the electric field energy density in a vacuum. It's just in a vacuum, we had an epsilon 0 there, in other words, the permittivity of free space. And now in this updated formula, we have an epsilon, the permittivity of the material. In the next video, we modified Gauss's law to work in the presence of a dielectric, and we solved the spherical capacitor with a dielectric filling the space between the plates. As part of that calculation, we're going to calculate the total energy stored in the spherical capacitor by integrating the electric field energy density. So we'll have a chance to put this new formula into practice. I'll post a link to that video at the upper left corner of the end screen, and I'll see you there.